Hey guys, morning. It's Monday, and we are going to finish chapter 3, which was about Bernoulli's equation, and we'll talk about additional topic, and then I'm going to show you how to solve bunch of examples, maybe two, and if I get time, I'll start chapter 7, which is the dimensional analysis. If you remember, we were talking about the Bernoulli we solve a question and the proof Bernoulli we will talk about the acceleration on a fluid particle, then how we can calculate and measure or calculate the acceleration, velocity, and then also we talk about the pressure and the Bernoulli's equation, how it's constant along a streamlines, and how we can calculate the pressure when the fluid has a velocity and the pressure is not always same as at the fluid at rest, which is the static pressure. Now today we're going to talk about Pitot static tube, which is useful and currently using on most of the aircrafts, and why we need that. At first, complete this figure. So if that's a Pitot static tube, but you have to know that these parts are full of fluids. Here also you have fluids. And if I cut this point, which is a prime, and show you here a fine face, you have this shape. These are the concentric tubes. And here at top you have point 1. And at the center you have point 2. What's the point of having two concentric tubes? The point is that here, if you have is the outer tube filled with the fluid, then you can say that this is only measure static pressure. Why? Because here the fluid is at rest. But here you will have a streamline. If that's a streamline and at point 3, the velocity is almost 0 because the flow comes up and stops here. If the flow stops here, then is going to be a stagnation point. What about this point? I'll put these R as 0. We are going to say that this is the upstream of flow. In fluid mechanics, the hint, in fluid mechanics, when fluid flow, then the flow moves from point 1 to point 2. This is all upstream, and this will be downstream. Okay. So that's the main question. We need why exactly we need the pitot tube? We need pitot tube to find static and stagnation pressure. Static and stagnation pressures. Why we need that? With these two, we can calculate the fluid flow speed. The speed can be calculated. How? So in upstream flow, here the velocity that we are going to calculate is the flow velocity, right? That's going to be the V. So we are going to find what is the velocity at point 0. At point 0, we also have P0, which is the static pressure at point 0, and Z0. In point 2, we have V2, which is almost equal to 0. Yeah, because the flow comes here and all these points are going to stop here and it's not coming up anymore. So when it's not coming up more, means the velocity at point 3 is 0 and also velocity at point 2 is 0. So velocity at point 2 is almost 0. We have P2 and Z2. At point 3, the same situation is the static and Z3. Okay, but we are making a strange assumption here, but it's not that much wrong because the size of this pitot tube is not that much big. So then you can consider that the elevation or rises of the fluid at point 3, 4, and 1 and 2 are similar. So delta Z is equal to 0, means Z at point 0 almost equal to point 1, point 2, and also at point 3. The delta Z's are 0. If you make this assumption, which is almost true, then elevation is negligible. And if you apply Bernoulli, between point 0 and 3, at point 0 along the streamlines, right? At point 2, 0, and point 3, all are at the same streamline. So the P at point 0 plus 1 over 2 rho v squared is equal to P3. So we cancel out the z's, and also v at 3 is 0. But if you see here, all 0.4, 0.1, and P0 are a static pressure, okay? So all are the same static pressure, because those are maybe the gauge pressure versus the atmospheric pressure. So a static pressure are the similar at point 0 and point 4, not at point 3, right? So then we can write that V, which is V.0 for flow speed, is equal to square root of 2 by 3 P3 minus P4 if P0 is also P4 over 2 rho. So it means that you are getting a pressure difference between 0.4 and 0.3, but as a result, you have velocity at 0.0. That's why, that's where the Pitot static tubes are used. That's a simple and inexpensive way to measure flow speed. And currently used in most of the aircrafts. Another example for a stagnation pressures, just as a hint for most of the question that you may see. When you have a symmetrical shape or object in front of the perpendicular flow, you will have a stagnation point at the start, at the front of these two objects. So this should be perpendicular to the object, and object should be symmetrical. And you can see here you also have, it's not that much symmetrical, the shape, or the flow is not that much perpendicular, but in large case it shows like this. But if you zoom in point here, then you can assume that the flow is perpendicular to a symmetrical object. To this line, or the streamline that gives you the stagnation point, is a stagnation streamline. The flow speed suddenly changed to 0 at this point. So you have velocity at upstream, but here the flow speed suddenly changed. to 0. That's why we mentioned this is a stagnation streamline, and that point is stagnation. But I missed here nothing. I told you everything. Any question till now? Okay, so chapter 3 is almost done, but I think that we need one additional topic that is not in Dr. Bataglia's notes, which is the confined flows. And it's useful when you want to solve a bunch of the questions in this chapter, and most of those questions you will see. So what's the point of confined flows? You can use the Pitot static tube to find the flow speed, right? But in nozzles and pipes with variable diameters, like the shape that you can see here, the diameter changes, right? So at point 1, you have A1, and point 2, you have A2, right? So for example, let's say you put the flow or put a static tube here. Then you, for example, very close to point 1. Then you have the velocity at point 1, right? But since the area is changing and the velocity are not constant, and the changes from 1 to 2 or passing through this pipe, then you should have Pitot static tube here, 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 and all these points to have a velocity profile as a function of x, right? That moving through that. This is not possible, right? So we need to find an equation for the velocity. When you get the velocity at point 1, you measure velocity at point 1, calculate velocity at point 2. How we can connect these two? We'll talk about that more in chapter 3, chapter 4 and 5, but just know that the rule for that, we know that the mass would be conserved, means that the mass you have here of a box of flow has to be here. It's not dissipate, it's not generate, so the mass is conserved. Then the m dot or mass flow rate that you have at this point should be equal to the mass flow rate of point 2, right? So here you have, we just give you an equation, but we will prove it later in chapter 4 and 5. That mass flow rate, which is the m dot, is volume flow rate times the density. So it's obvious. You have flow, the mass that you have at the specific time passing through this area, it has to be equal to the mass that passes through this area at a specific time. Okay, just check the units. The Q is also can write the Q, but it has to be Q dot. I'm not sure why the book used that, but doesn't matter. As long as that you know the meaning. Volume flow rate times density is the mass flow rate. The Q is volume flow rate, has the rate, so it means over second. Volume is meter cubed, right? Density is kilogram per meter cube. And if you check the unit for mass flow rate, we multiply these two. Meter cube going to be cancelled out with meter cube, and the mass flow rate is kilogram per second. What does it mean? It means that how much mass of fluid passes through an open area in a specific time. That makes sense, right? So how we can prove it in simple way? So when we're talking about the rate, it means that delta t or time should be very small. Okay, that's the meaning of small in rate means small. So specific time means that delta t should be a very small amount of time change, but you have to have because you want the flow path, right? So if I get a specific area or any a specific line or any point at this nozzle, and the area is A, and you let the specific time or that delta T changes from 0 to delta T, then you have a flow at the area of A that after delta T moves delta X through channel, right? Moving forward. How much is the volume of this box of fluid that passes? Volume of the flow that passes or the area times delta X. Since you can see the delta X is very similar, very small, then you can assume that delta X is like a circle or very thin cylinder. Then delta X going to be height of that cylinder, and area multiply delta X going to be the volume of that cylinder, right? Okay, so 8 times delta X gives you the volume, and that's only volume. But what is the volume flow rate is over the time. So 8 times delta X, which is your volume time over the delta T. But delta X over delta T, you can replace it by velocity, right? Because this means velocity from fluid that passes delta X over delta T time. So I replace that with A times B. That's the Q or volume flow rate. And what is the mass flow rate? Mass flow rate means that we multiply the with rho density, right? If you multiply, we checked it here, the units as well works. So multiply that by rho AV is your mass flow rate that pass through this area, right? Let's come back in here. You put the Pitot tube test here. You get the velocity at point 1. How you can calculate velocity at point 2? If you know what is the diameter or area at point 1 and point 2, then you measure the velocity at point 1, and you can assume that most of the fluids that the rho is constant, right? Or doesn't matter. You know what is the rho at point 1 or point 2. The rho 1, A1, B1 is equal to rho 2, A2, B2. That's the meaning of the mass is conserved. So you only need that sometimes applied in the questions because of the confined flows. You cannot absolutely have 2 or 3 or n number of Pitot tube tests over a confined flow in a nozzle or the pipe that the diameter of that continuously change. Okay, any question till now? Okay, let's move forward. So here is our example 1. I know that talking about the rules, talking about the improvement of equations is not useful always. You have to solve and solve and solve questions. So the more question example that I'm solving for you and show you how you can solve and decode the equation, and then know that which equation and how you can attack this question, it could be more helpful for you. Here is an example. The investigating compressible liquid flows steadily from a large pressurized tank. Determine the specific gravity of the fluid or liquid. So what is asked that what is the gamma? Ask what is the specific gravity. So SG is requested. Well, anyway, it actually asks you what is the density of that. So what is the SG of liquid, right? That's the question. Well, let's summarize the assumption. First is inviscid. Second is incompressible. It steadily flows from a large pressurized tank. It gives you two hints. First, steadily means that it continuously comes in and over the time, because the tank is very huge, or huge amount of liquid you have. So you can assume that the flow is steady. What else it gives? When you have a huge tank here and you have huge amount of liquid here, then in the time that you are talking about, the flow, this flow is steady, right? Steady means that if you freeze the time and take a picture of that, and then in rational time again let it pass and freeze it and take another picture, these two should be similar. Means similar means that the height of change of height here is not much, right? If the height change is not much, then velocity of this surface of the liquid that comes down is almost zero. If we say that that's the velocity of this point that's coming down. These two can be understood from this equation, the equation or sentence. First, let's summarize the assumptions. The first assumption is a steady. Second assumption, inviscid flow. Third assumption is incompressible flow. And what is the fourth assumption to apply Bernoulli? Longest similar, right? This is up to you to find the similar and apply it. As long as you remember the fourth one, you are good. I will clear that. My reference Z at this point. That's my Z, or reference point. Okay. And I will consider a streamlines that comes through it. This is the point one, and that's point two, right? Based on these two, at point one, V1 is 0, right? What about P1? P1 is measured here, but that's a gauge pressure, right? So P1 is 70 kilopascal, but as a gauge pressure. If you see this thing, it gives you the gauge pressure always. Doesn't mention the question, but remember that this is the gauge pressure. At point two, V2 is 12 meters per second, right? And P2 is P atmosphere. P atmosphere is absolute pressure. If you write that, okay, here is ambient, and that's my atmospheric pressure, okay. You can write the atmospheric pressure, but remember that is absolute pressure. Or at point two, gauge pressure is 0 kilopascal. That's your gauge pressure, okay? Or also you can connect these two with that, okay, I have P atmosphere here, okay, I'll keep it. But what is the absolute pressure at point one? The absolute pressure at point one is 70 kilopascal plus P atmosphere. Okay? Use P atmosphere, the absolute pressure or gauge pressure in Bernoulli, but keep that similar and same in your the whole streamline and equation that you write. Okay, so let's apply Bernoulli between these 2 points. Apply Bernoulli's equation. The first is P1. I'm using the absolute one. P1A plus 1 over 2 rho of the liquid V1 squared plus gamma Z1 should be equal to P2 absolute plus 1 over 2 rho LV2 squared plus gamma of the liquid times Z at point 2. Okay, and using those, can I replace that PA, P1 at A is 70 kilopascal as wrote here. So 70 kilopascal plus P atmosphere. What is V1 is 0. And Z1, I put the reference there. These two are 0. What else I have at the other side? On the other side, I have P2 absolute. P2 absolute is P atmosphere plus 1 over 2 rho L. And I know that's 12 squared, right? 12 meters per second at point 2. And plus gamma of L times Z2. But Z2 is available here. One as from Z2, if that's our reference, then 4.5 or some negative is your Z, right? So times minus 4.5. That's why I told you the P of the absolute or gauge doesn't matter, because as long as that you are using the same, if you add P atmosphere in both sides, then these two are going to cancel. If you only use the gauge pressure at this point, but remember to, when the flow comes to the ambient, you also add the same amount or P atmosphere equal or P gauge pressure here 0, then you are good. Okay. So let's calculate now. The rest is calculation. You need only one calculator for that. So 70 kilopascal minus, I bring the whole terms on one side. So this is going to be 144. 144 over 2 is 72. So minus 72 rho of liquid. And also minus comes going to be positive rho of liquid times 9.81, which is your G, times 4.5, right? I just put the negative sign, I get rid of the negative sign. It has to be equal to 0. Then the rho of liquid is equal to 70 kilopascal, which is kilonewton per meter squared, over, if I calculate these two, because the only rho L is equal in these two terms, then minus 27, which is positive from the other side, 27,885 meter squared over s squared. That's the unit for the velocity to the power of 2, meter over second to the power of 2, or using these two, meter times meter over second squared. Again, gives you the same. If you check the units, and that's your rho, right? Before calculate that, let's check units. kilonewton, you can replace okay, kilo is nothing important because you multiply that by 1,000. But Newton is Newton per meter squared times, bring this unit on top, second squared times meter squared, right? But also you can replace Newton with kilogram meter per second square over meter squared times second squared over meter squared. You can cancel out these two and 1m from this. What you have, you will have kilogram per meter cube, which is the unit for rho. Okay. Then homogeneity of the dimension is valid here. Okay, so what would be your L? Well, by calculating that, rho of the L is equal to 2,510 kilogram per meter cube. What would be your SG that the question asks you? Calculate. Sg of the liquid is equal to gamma of the L over the gamma of water, right? Okay, so 210 over thousands, you can spell that for the water, is equal to 2.51. Okay, any question till now? That was simple question, almost simple. But let's have the second example, which will tell more hard and it's more challenging. Example 2. We have a nozzle here that from hose of this nozzle, the flow discharge, the vertical jet, and the flow is oil with SG of 0.85. And here is ambient pressure or ambient, the flow discharge in ambient condition. So the gauge pressure at point A is 45 kilopascal. It's given. The hose diameters are given. dA is 0.2 meter and dB, which is the outlet diameter, is 0.1. And the distance between point A and B is 1 meter. So the difference of the Z also is given. What it asks you, it may give you that how much is the height here. The height that the jet comes up and reach the dead point or the maximum point. So I'll write the point C here. This is the point that absolutely should be considered because we are going to find the Z of that, okay? And also you need a reference Z. I put reference here. Nothing gonna change if you decide to put Z here. Just remember that whatever you are calculating or putting for Z of C now is H plus 1, right? For B is 1. But I decided to put it here. So the Z reference is nothing important because it's going to give you the same answer. That's my atmosphere. But remember, this is not ambient. It comes from the hose, right? Here is also my streamline. So point A, B, and C, if that's my streamline, point A, B, and C are on a streamline. The only thing that we need to write here is SG of the liquid, which is 0.85. Okay, so let's list assumptions at first. The first thing that you have to do. What is the assumption? The first assumption is that's oil, and you can consider is incompressible. Two, is invested, you can apply it, okay, because of the type of the oil that you have. And nothing mentioned that again, you can assume that is invested. Absolutely, it's not perfect assumption, but here it mentioned that the losses are negligible, right? What are the losses in a channel? Mostly because of the viscosity. Because of the viscosity, the flow layers are there is a friction between those, and that's the meaning of losses, right? The friction. Because it mentioned that the losses are negligible, then you can assume that the flow is also in this. Okay. But you need chapter 8, 9, that is the pipe flow, to understand it. But for now, you can say that, okay, there is no losses, so there is nothing between the layers of the fluid. I can assume that this is invisible, right? And this is up to you to mention, okay, how much fluid passes? The fluid passes comes from a huge tank. That's my assumption. So always this shape of the jet is available in time, or the time that I'm talking about. So time is not mentioned anymore, anything about the time here. And I'm allowed to consider that is a steady state. Sometimes for this assumption, you don't have anything to reject it, right? So that's my assumption. There is any reason to consider this is not steady state? No. So I will consider that a steady state because this gives me an opportunity to use Bernoulli. Okay, so why not? And finally, it's up to me again to use on a streamline, longest streamline that obviously here also showed that these three are going to be on the same streamlines for the points that I'm going to use. What else I'm going to show you here? At first, the P at point C, the gauge pressure is equal to P of the B gauge pressure because both of them are ambient pressure. And ambient or atmospheric pressure is equal to zero. The gauge pressure would be zero. So what we know and what we don't know about these 3 points, let's write them. Let's list the unknowns. At point A, we have PA of the gauge, PVA, and Z of the A, right? The height. At point B, what we have P of the B, gauge pressure at point B, V of the B, and V of the B. At point C, what we need, all parameters. So PC of the G, V of the sea and Z, height of the sea. What we know from this? First, we know these two are zero, right? So we know it. No. What about C? We know that velocity at point C is zero, so we know it. This is the thing that asked by the question. So we don't know what is it. We have to find it. We know what is the ZB. Yes, we put the reference point here. Well, what about the velocity at point B? Don't know. Height of the A, yes, it's given that how much is the difference between point B and A. Since we know what is the Z of B because our reference point is here, so we know ZA. But we know what is the velocity at point A? No. What about the pressure? It's given. How many unknowns I have here? 1, 2, 3. So at least 3 equations, independent equations are needed to solve and find it, right? If I have an equation that relate H to a bunch of or nouns, yeah, you need only one. You don't need to find VA, you don't need to find VB, because the question asks you what is the H, and only thing that you need to put a box around it is the H, right? But do you have an equation for H? If you know, okay, so one equation is needed. But you will find out that you need all these three. From all these 3 points, you need a bunch of the knowns and unknowns to, connect and step by step find H. That's why I'm thinking it's better to write the knowns at these 3 points. So at least 3 equations are needed. So where I should bring these 3, okay? So one is the Bernoulli between point A and B. Second is Bernoulli from A to C. And what about 3? How we have the third one? Can I write Bernoulli A to B and B over C? Yes, we can do it, but this is not gonna give you anything more than A and B. If you cancel out those, you will find out, hey, 2 equations are the same. Because between these 2 or 3 points that are on the streamline, you can write between A and B, and then B and C. But again, apply that between A and C is not going to give you anything independent equation. So it's not useful. But we know about the compound flows. We know that m dot at point A are equal m dot at point D. How I can find that the m dot should be used here, right? First, the diameters are changing, right? And also the diameters are given. So there is a reason behind that, that is given, okay? These are the hints in the question. That's why reading a question and understanding that is 50% of solving the question. If you completely understand the question and decode the sentences, you almost have faith passing solving that question. Okay, these are the hints. So by doing that, m dot A and m dot B are equal, right? To summarize all knowns, we know what is the oil is 0.85 or rho of the water, which is a meter cube, and the gamma of oil is rho of the oil times G is 38.5. Okay, that's the gamma. Wrote it here. The G is 9.81 meter per second squared. Top. I have a clear version of this one, and I will upload the notes. Don't worry about how bad I'm writing here, because it's so hard to keep for me, because of the size of the table and it's close to the wall. I cannot keep the page straight and also writing straight. That's very hard. Okay, let's write the equation one. Equation one is Bernoulli between A and B, right? Okay. PA of the gauge plus 1 over 2 rows of the oil, VA squared plus oil Z of A should be equal to PP of the gauge plus 1 over 2 row oil, VB squared plus comma of the oil, ZB, right? Equation 1. What is equation 2? Equation 2 is between A and C, right? Okay. Again, P of the A engaged plus 1 over 2 row AVA squared plus gamma oil ZA is equal to PC of the gauge plus C. And equation 3 or M dot is constant, right? Okay. What's that? Rho of the oil times area at point A, rho V A. That's better to write in this way. VA times area at point A, right? Area at point A, this is a circular shape. And for the circle is pi d over pi d squared over 4, right? Pi dA squared over 4 is equal to rho of the oil V of the B times pi dB squared over 4. Okay. What is the known and what is zero in these two equations? First, these two are zero. These are gauge pressures, right? Our reference point is here. This is zero. We mentioned on top that this is the peak point. At peak point, the velocity of jet is zero. So we see also zero. I also can cancel out the raw oils from each side. And that's it. That's all numbers. Okay, so what is if I rewrite this? Bring VB, keep VB at one side, VA, and the other side. Also, I can cancel out pi and 4 from each side. Okay, VB over VA is D A squared over DB squared, or DB over DA squared. So VB over VA is equal to VB over VA is equal to DA over DB. DA is 0.2 and DB is 0.1. The power of 2 is 4. So yes, that's it. VB is 4 times VA. Right. Keep it here on top of the equations. One more page. Okay. if I use the results of equation 3 in equation 1 and 2 and replace it, then I can replace or plug in equation 3 in equation 1, right? Equation 3, which is here, is just replacing or changing VB and VA, make it the same, right? So if you change it, then so what are the unknowns? We know what is the ZA. We know what is the pressure at this point, right? The only thing that we don't know from these two equations is one unknown is VA. You have no idea about it. And also we don't know what is the ZC. That's because it's or H, right? The rest are no. If you find and also VB, you have no idea about it, right? But if you replace VB and connect it to VA, then the only unknowns, instead of three unknowns in these two equations, you have two unknowns, and then you can solve. That's why we need VA, the relation between VB and VA. Okay, so if I replace 3 or plug in 3 on 2, then PA of the gauge plus 1 over 2 rho 0 VA squared plus gamma oil VA is equal to 1 over 2. So these two are 0, 1 over 2 rho. Instead of VB, I put 4 AVA squared. To make it easier, I will multiply each side in 1 over gamma oil and make all equal to 0. Bring the right hand side to the left hand side and make it 0. Okay, so what would be the result? G over gamma of the oil plus is going to be VA squared over 2G. Why? Because gamma is raw oil times G, right? Is going to be gamma of oil, right? And if you put this in denominator, the rho of the oil going to be cancelled out for rho of the oil, and you have 2 and G on the denominator now. So VA squared over 2G. And you can bring this on also here and multiply that 1 over gamma oil. We will have 1 minus 16, 4 to the power of 2 times VA squared now over 2G plus gamma of the oil. Now we cancel out the gamma of the oil and ZA is not, is equal to 0, right? Rewrite that P of the A of the gauge over gamma of the oil plus, not plus, it's negative now because you have 16 negative of it. So minus 15 VA squared over 2G plus CA are equal to 0. If you plug in T into, you have PA again of the gauge plus 1 over 2 0 VA squared plus gamma of the oil ZA is equal to gamma of the oil ZC. Why? Because these two are 0. Again, do the same. 1 over gamma oil and all equal to 0. And also replace the ZC is H. That's or something that we are going to find, right? Okay. PA of the gauge, pressure over the gamma of the oil plus VA squared over 2G plus VA minus H equal to 0. I put 4 here, 5 here. Okay, I know PA gauge, but still doesn't know what is a VA, right? So using equation 4, and first find VA. So VA squared, so VA squared is using the VA that is known and the other are known, right? So it's going to be 2G 9.81 over 15 times 45 kilopascal over 833.8.5, which is all gamma of the oil, minus 1 meter. Then VA square is 5.75 over 2, and then VA is equal to almost equal to 2.4 meters second. You know VA now. Now plug in VA in equation 5 and then find H. Equation 5 is here. So 45 kilopascal over gamma of the oil, which is 8838.5 plus VA squared over of 2 over 2 cross 9.81 or G minus 1 is equal to H. Then H is equal to almost equal to 4.7 meters. Any question? So that's also second example. If I had time, I'll show you need to solve more questions. But I guess for now it's enough. For the homework also you will do at least 2, 3, or 4 questions by yourself. And that would be helpful. Because we are just a little behind, that's not a good idea to start a new chapter at the end of a class, but we need it. So that's dimensional analysis. That simple thing, we'll review it again in the next class, but just to have a background for starting next class, let's just review it. What is the similitude, dimensional analysis, and modeling? So we are in chapter 3, but we jump on chapter 7 or finish it, then coming back for chapter 4 and 5, because you need the dimensional analysis for that. Also, it's one of the most important chapters here. And you will never find out about it in the rest of the fluid mechanics if you don't understand it right now. Okay, so often problems are solved using experiments and theory. It's obvious. We are doing experimental fluid mechanics. And the experimental fluid mechanics is you have two types: numerical simulations and experimental simulation, experimental study. Numerical study is just using the equations and modeling the softwares like CFD methods. But experimental is half of this study, the fluid mechanics. So experiment is important, and What important is the experiment is that how your experiment exact, how you can replicate the real case situation, and how you can be more can be confident about your result. Such a combined approach uses the technique based on the dimensionality, simulate, and modeling. That's the meaning of experiment, using these three in a row. A dimensionless number that I gave you an example for that, which is the Reynolds number. And if you remember, we added additional topic in the chapter 1, and we talk about the Reynolds number, and because that's one of the most important dimensionless numbers. Okay, so the same as Reynolds number, a dimensionless number is a ratio of quantities, right? So Reynolds is rho v L over mu. These are quantities, right? The ratio of quantities that form a product without dimensions, like Reynolds number, right? What it represents? It represents scaling between physical processes or phenomena to help us determine how different situations can be related for research or design. Maybe sometimes we find that, okay, these are doesn't make sense, right? Uh, what does it mean? A dimensionless parameter, and how these two, or how is going to show that, or we are simulating the real case in our experiments. But when you find out the examples, maybe, and you need to, we have to talk about more examples here because absolutely this chapter is new for you. We'll talk about it later in the next class. But for now, just keep that it works. You need the dimensional numbers to see that how you are um, make a correct situation the same as ideal cases or ideal situation. We'll example that when we find out. So dimensional analysis for a given problem, it means that you have to identify variables that first affect the quantity to be solved. It's not easy. Believe me, it's not easy. For example, the flow passes through a channel. Just list parameters in your mind. What parameters are affect the velocity, for example? Okay, so do I need to consider the temperature or not? Do I need to consider this geometry or the diameter of the channel? Yes, you have to. But yes, let's consider that, okay, the mu absolutely should be there. The diameter of the channel, yes. What about the temperature? Or how can I say that how much the result of the velocity are dependent on the temperature? How these are changing with each other, okay? So this is hard. And you need experiments to find out how much each of these parameters are affect the results. But for now, at least you know you have to list and find the parameters, right? The variables that are affected result. At first, you have to know that what are available variables, right? This could be the geometries, could be external effects, and also could be properties. These are all type of uh, available variables, right? The geometry is like L length, like D diameter, like angle, right? Sometimes the angle matters, and something like this. What about the external effects? External effects like velocity, pressure change, right? That's why it's also important. For example, the flow pass through a channel. The pressure change is important, right? The temperature, yeah, sometimes important. What about the properties? The properties are like mu, rho, nu. These are type of properties, right? These are also important. But that's the question. How we found that which one is? If, for example, you are going to give me a model that's going to be perfect for finding that pressure difference, right? For example, you have a vessel, right, in human body. You make a vessel, that's an in vitro test, right? You make a model of that. Now you put blood in one side, and then in the next side of that vessel, which is a pipe. Now you'll find out, you are going to show me how much is the pressure difference, right? At first, I will ask you, okay, the pressure difference is, you need to give me an equation, right? To find what is the pressure difference. Equation means that give me delta P as a function of bunch of the variables, right? First, you have to list it. What are the available variables, and what of those, how many of those are affect the pressure difference? So at first, to find out, you need experiments. How you are doing the experiments? You first keep delta pi, keep track of it, keep others constant, like diameter, rho, v, whatever you listed, and then only change one of those. Sometimes changing one of these parameters, we cannot keep the others constant, right? So these are changing together. For example, if you change the temperature as a parameter here, then you cannot keep the mu and rho constants. These are moving together, right? So sometimes that's why that would be hard. But if you have a non-dimensional model or non-dimensional term, then tracking that would be easier. That's why Reynolds is a parameter or variable, non-dimensional parameter that will help you to compare different models, right? And that's why it works for finding that you have in transitional between the laminar and turbulent. Also, you are in turbulent flow or laminar flow. But that's the method that you find out what is the pressure difference as a function of the others. So you keep each time, you see, here you only change mu, the rest are constant. In the next step, you keep mu constant, now select the other one, which is V. And here, mu and V are constant, you keep rho and D absolutely. In the next one, you have to keep D, mu, and V constant and bring the rho as another parameter, right? And sometimes you need that, okay, by this changing, for example, pressure difference for mu is like this. Then you will have also meaning of sensitivity of delta P to that parameter, which is rho, for example. These are also examples. That's why we need. So after doing that, you need to connect those parameters and find dimensionless quantities, like called Pitot, pi term, and is based on Buckingham Pitot, right? We'll show it with the capital pi. It's in Greek, and it shows like this, okay? For example, you have R equal, then you have R reference dimensions, right? Reference dimensions is like MLT. If you are in MLT, it would be ML and T, which is time, length, mass, plus could be temperature, right? And if you are FLT, you have force, length, and time, and plus temperature if needed. These are your reference dimensions, right? Absolutely. Any parameter in fluid mechanics is related to the time. Okay, time would be one. Length and mass are the others, right? Or force as a combination of those. These are the reference dimensions if you are doing that processing in MLT or FLT, right? One of these. But you will have mu. Mu is not the reference parameter, right? So it's possible to have k equal number of variables now. So variables could be mu, rho, d, diameter, which is diameter is length, right? In the term of length. So that would be your reference parameter. But reference parameter also is type k variable, right? So d could be one, L could be one. These are all your variables, right? Doesn't matter that these are the reference dimensions or not. These are the variables that affect, right? Mu, rho, d, L, maybe temperature, maybe whatever. You're just listing. How you can find the pi term now? You will list all your variables, okay? And then you have two MLT FLT system to as a reference dimension, right? So you have to express all your variables in form of MLT using MLT and FLT, right? We did that in chapter 1, that how you can show the, for example, acceleration. For example, acceleration, if you are showing that in form of the basic dimensions is going to be meter per second square is going to be mt minus t, right? That's the form that you have to show. You will show all lists of variables in that. Then you have to determine what is the number of pi terms. So pi terms, if based on the Buckingham pi theorem, the number of pi terms would be k minus r. Listed variables minus the main dimensions, right? If k minus r gives you that how many of those non-dimension parameters you will have, groups you have. The next step is that based on R, you will have to select R variables to be used to non-dimensionalize the other variables. So this means that what are sorry, let me. Yeah, we will talk about. Yeah, one of your friends asked me that what is Buckingham pi theory, right? This is the Buckingham pi theory that I'm talking about. That loop that we are doing is the Buckingham pi theorem. Buckingham pi theorem. That's why that I'm just reviewing that. We will talk about it in detail next uh, class. But you want to know that what is the pi theorem, right? The pi theorem, Buckingham pi theorem, is this method. How you have to connect these two and find finally the non-dimensional groups. This is the method of pi theorem. I hope it answered your question. But yeah, I know. Just be patient, guys. This chapter is always take more time in meaning, and the method is the most easiest chapter in whole fluid mechanics, right? It's very simple, but we will put the most amount of time for this chapter. The reason is that exactly for the first time, some of you asked the questions, right? That, hey, you're not familiar with that. Yeah, I know, because this is the new topic for you. But you have to be patient. But if you be patient with that, you will find that, oh, that's sweet. It's simple. It works all the time, and you have to be, this is like art. You have to bring the variables, somehow connect these to find the non-dimensional groups, and then play with the units and make sure that this is dimension, what is the dimension, the homogeneity of the dimensions, and find the groups. That's why when you have a new topic, when most of the science works, like researchers, you have to do the uh, dimensional analysis and the pi uh, terms, finding the non-variable, non-dimensional parameters, and then play with it, right? But also, I'm going to, I wanted to reach this point, and we have to finish the class, but I want you to review 7.1 to 7.5 and read this section and have a background, because that's, I know that this is new topic for you and you have to know a little bit before when you're coming to the class. We will talk about the common dimensionless groups, and absolutely we have to solve a bunch of the questions, a bunch of examples for you to more understand more. Thank you guys. That's enough for today. I hope it gave you a background or introduction and also the chapter 7. Any question?